Hi everyone. I had a technical difficulty today while recording the second part of the lecture. And in addition, there was some strange delay again, like we used to have. And so I think this is happening now as well. And so I decided to just stop it and refilm it. So here we go. So now we need to discuss something called operators and expectation values. That's the next bite-sized piece of information, and you need this for homework 9. So expectation value is just a fancy name for average. Okay, quantum mechanics gives you a distribution of values, you get a distribution of outcomes, and the average of that distribution is called an expectation value. But what's an operator? An operator is something that performs some operation on a function. So for example, multiplying a function by x is an operation. So you start with f of x. There's a delay, I don't know why. You start with f of x and you end up with x times f of x. That's a different function. So for example, if the function is sine of x, performing the operation of multiplying by x gives you x times sine of x. It's a different function. So you start with a function, you do something to it, you operate on it, and you get a different function back. Example 2, taking a derivative. Taking a derivative is performing an operation. You start with a function f, and it spits out the derivative of f. We say that this ddx is a derivative operator, such that when it hits the function, it gives you a derivative of a function. So a graphical way to represent an operator is that it's like a machine. It's a machine. So this is called an operator. You put a function in and you get a different function out. It's a machine. So on that note, generally, we say that there is an operator O hat. We put a hat to indicate that it's an operator, not a letter, not a number, not a variable, not a function, but an operator. Generically, I call it operator O hat, that performs some operation on a function f, and the result is some other function g. In other words, I can take this picture and I can redraw it, right? I can say that I have some kind of a function f. It enters the operator, or I like to use the language, an operator hits the function f, and it spits out a different function g. Mathematically, you'd say g is the result of O hat operating on f. Here's f, boom, O hat hits f, something else comes out called g. So for example, let's say f of x is x squared, and the operator is the derivative operator, ddx. Then, when operator ddx hits the f, right? So abstractly, you write it like this, but concretely, you write it like this, which is what? ddx of x squared gives you 2x. So here's your g. You start with f, you end up with a different function g. Here's a different example. multiplication by x. For example, x could be a position. And let's say you have, again, the same function, x squared. I'm using O prime to indicate that it's a different operator, right? So not to confuse this operator with this operator, I'm using a different letter, O prime. Okay, so it's a different operator. What does this operator do? It multiplies the function by x, simply just tags on an extra x. So when O prime hat hits the same function f, we get this, we get a different function g. Okay, you can take a function f and attack it with different operators and you're gonna get different functions. Okay, so that's math. Why? So here's why. This is a big deal. It's like a, think of this as a postulate. To every measurable quantity, which is often called observable, something that you can observe. Mass is an observable. Charge is an observable. Position is an observable. Momentum is an observable. Angular momentum is an observable. Energy is an observable, and so on. To every observable or to every measurable quantity in quantum mechanics, there corresponds an operator. For example, to a position measurement, there corresponds a position operator. What does it do? It multiplies the wave function by coordinate x. Right? So what does this position operator do? So when x attacks the wave function, it simply gives you x times the wave function, because the wave function itself is a function of x, right? So that's the action of the position operator. Example 2. To a momentum measurement, there corresponds to a momentum operator, P. We will see what that momentum operator, what it does in a second. But it's some other operator that does something else to the wave function. It massages the wave function into some other form. It does something else. Okay. Next topic. I mean, next subtopic, right? So I explained what an operator is. I connected it to quantum mechanics, but it's still too abstract. Bear with me. Here's the next big idea. An average value of an observable described by an operator O hat, that is an expectation value of a measurement that's described by an operator O hat on an ensemble of systems, all described by a wave function psi. That expectation value is given by this formula. Okay, and this deserves a box. Okay, see if I can. So you have, let's digest this. We have an ensemble of identical systems, say harmonic oscillators. You place each one in the same psi, say ground state. And then you start measuring away. Let's say you measure position. You can get one value in one system, another value in another value in another. That's what we talked about yesterday. You're going to get a whole ensemble of results, a set of results. I want to know the average of those results. That average is called expectation value. It's just an average or a mean. I don't know why there's so many synonyms of the word average. If we have the math, if we know the wave function, big psi, we can predict what that average will be. And this is how you do it. You construct a sandwich. Psi star times the operator acting on psi, and you integrate the whole darn thing between left and the right end. For example, let's say I have a wave function, big psi. I perform position measurements. I want to find the expectation value of position. Here's my sandwich. Psi star times the operator x, which just multiplies the thing by x times the psi. I can rearrange it, okay, and I can make it look like this. I can move the x around. Everything is just a function of x, right? This is a function of x. This is a function of x. And you recognize that this is this, and you say, well, I've already done this calculation. Yes, I'm casting what you already know in a different language for a reason, for a reason, of course. Example 2, momentum. We already discussed how to compute the expectation value of momentum. I gave you this formula. Okay, you had a video quiz question on it. Construct a sandwich. Psi star times minus IH bar times the derivative of psi. But now that you know about the derivative operator, you realize, oh, this is just a derivative operator. And now that I've told you about this, you can put everything together and you can define a momentum operator. It's minus IH bar times the derivative operator. And you realize that you can rewrite this expression like this, which fits this general idea right here, the blue box. Okay? So in terms of the operator, the expectation value of the momentum is given by this formula, which is equivalent to this expression right here. Okay? I'm gonna pause, and then you should pause some more. Take a deep breath. Okay. So that's operators and expectation values. Next subtopic. Let's recall the time-independent Schrödinger's equation, this thing right here. This thing right here, the top blue thing that I'm circling right now. Now that you know about momentum operators, you realize that, well, without the hat, right? You realize that, well, this first set of terms is really just momentum operator squared divided by 2m. And I can define also the potential energy operator U hat. Sorry, let me write it like this. I can define the potential energy operator. What is a potential energy operator? It takes the wave function and it multiplies it by the potential energy, just like the position operator just multiplies the function by x, okay? So I can define here, let me define in blue, potential energy operator hitting the wave function just gives you the potential energy times the wave function, okay? Just like x hat operator just multiplies the function by x. So you have multiplicative operators that just multiply the function, and you have differential operators that take some kind of a derivative. And so you recognize, so I can cast the time-independent Schrödinger's equation in this interesting form, in the operator form. And why would I want to do that? Well, before I answer that question, this whole darn thing right here, this whole thing, the square bracket, is some kind of an operator. It has a name. It's called a Hamiltonian operator. I'm gonna pause, I'm gonna erase something here. So this whole thing is called H hat. Hamiltonian operator. let's digest. What's the meaning of this Hamiltonian operator? If there was no Hertz, it looks a lot like something we already know. In classical mechanics, p squared over 2m plus u, well, this is kinetic energy and this is potential energy, not operators, in classical mechanics. You might think that this gadget is called energy. It's called mechanical energy, right? Kinetic plus potential. But for certain reasons that we're not going to discuss, in some circumstances, this combo, when it's written like that, when you write kinetic energy plus potential energy in this form, it's called a Hamiltonian. You haven't taken classical mechanics. Some of you will. You will understand where this name comes from. But basically, it's energy. Okay? In quantum mechanics, it's promoted to an operator. So that's why it's called a Hamiltonian operator. But it's basically an energy operator. Okay? So Hamiltonian operator is basically an energy operator. Okay? Let's just, for practice, try to compute. Let's compute the expectation value of the Hamiltonian operator on a modal wave function. Okay? So modal wave function is the spatial part, e to the minus I omega nt. That's a modal wave function, right? Spatial part and the temporal part. For example, it could be the nth mode of a harmonic oscillator, nth mode of atom, nth mode of a particle in the box. Just for kicks, just it will serve us some purpose, but also to get you accustomed to what are we doing? These are all weird things, right? Let's try to do that. I'm not going to write the limits. I'm too tired, and you're too tired too. Okay, so I'm just going to say, I'm going to construct that sandwich. Well, so first of all, let me expand this. In general, the spatial part can also be complex. And the first thing I'm going to do is I'm going to move these guys around until I'm going to move the temporal factors around until they multiply to 1, because this operates only on the spatial part of the wave function. It takes a derivative, multiplies by u of x. It has no time reference in it. So I can move the temporal factors around. And let's remember that these are all functions of space, okay? There's something definitely wrong today, technologically. I'm not sure why there's a delay. It's very frustrating. And we just saw that the Schrödinger's equation can be written in a compact form. So Schrödinger's equation can be written as Hamiltonian operator acting on the wave on the spatial part of the wave function gives you E, which we agreed is energy, times the spatial part of the wave function back. That's really your time-independent Schrödinger's equation. In operator form, it's very compact. It has this very interesting feature that when the Hamiltonian operator hits the wave function, it gives back the wave function multiplied by a constant E. And that's exactly what we have here, right? So you see we have this. And you're not watching this for no reason. This will be useful for you in doing one of the homework problems from the textbook. So you get, I'm not gonna write the functional dependence x. E times the wave function back. But this is just a constant. I can take it out of the integral, right? And I get this. And we're being good sports. We have normalized all our wave functions, that this is 1. So the expectation value of the Hamiltonian operator is this E, okay? So on the one hand, the expectation value of the Hamiltonian is this constant E. Where does this constant E come from? Okay, I told you it's energy, but why? Remember, it really came from doing the separation of variables, and it's just a separation constant. Okay. On the other hand, expectation value, the Hamiltonian operator is the expectation value of a p squared over 2m plus the expectation value of the potential energy, which is just the expectation value of energy. And that really is the reason why we interpreted E as the energy, the separation constant as having the meaning of energy. By the way, kinetic energy operator, if you look at this, this is the kinetic energy operator. It's what you would get, it's how you would write the kinetic energy in classical mechanics, but you promote P to a status of an operator. So instead of writing P squared over 2m, you say it's P hat over 2m. But P hat is what? Minus I h bar for partial x whole squared, which is minus times minus is a plus, but I times I is a minus, which is minus h bar squared over 2m times the second derivative. Yes, you can multiply derivative operators and turn that from a first derivative to a second derivative. First derivative squared is a second derivative. It works just like that. I will have a few more things to say, but I want to give you a little pointer for your homework problem. So in your homework problem, I believe this is problem number, this is chapter 5, exercise 66. They give you a superposition state of 2 modes. So what I just did is I computed the expectation value of the Hamiltonian operator, of the Hamiltonian, or the energy, in a pure mode. Let's take it up a notch. So what they give you is they give you a linear combination of 2 modes. 1 over root 2 psi n of x e to the minus I. I'm going to call it omega n, but they write it as en over h bar. You already know they're the same. It's 1 over root 2 psi m minus omega mt. And these are infinite well modes. Okay? So compute the expectation value of energy. There are 2 ways to do this. Method 1, just apply what you know. Folks, you know quite a lot. You just have to trust, you have to keep track of what's the basic principle, right? So this idea that an expectation value from a measurement is given by this sandwich, that's a basic principle. So what this means is a Hamiltonian operator acts on the wave function, returns something else, you multiply by psi star, and then you integrate. It's not as scary as it looks. So let's operate with this on the wave function. Hamiltonian only acts on these guys, remember? So for time there are time dependent Hamiltonians, but in this case, we have a time independent Hamiltonian. It leaves this guy's intact. And what happens when you hit the spatial part of the wave function with the Hamiltonian? You get that wave function back times E, that according to the time independent Schrödinger's equation. So you get 1/√2 E sub n times the wave function n back. I'm not writing its functional dependence on x. Right? And then we need to multiply it by this guy. Just like in your previous homework, which is why it was so important to do the non-textbook problem in homework 8, and which is why it appeared on the quiz, is to give you a practice. So psi star times h psi, and this is the h psi. So you have operated by the Hamiltonian operator on the psi, and this is the result. It's a different function because it has the e's now in the numerator, equals a sum of how many terms? 4 terms. And then you use this property. Since these are modes of a particle in the box, you're going to get sine squared in the nth state, sine n pi x over L squared. And then you're going to get sine squared of the mth state from the mth state. And then you get 2 cross terms, sine n pi x over L times sine m pi x over L, and then the other cross term. And so it will come handy to know, well, first of all, this is true because these guys are normalized, pre-normalized. That's why there's a square factor of √2 over L that ensures the normalization. So at this point, you can just profit from your knowledge that these guys are normalized. And obviously, this guy is also normalized. Okay? That's why it's good to normalize each mode individually. And let's see, psi n of x, psi m of x, dx between 0 and L is 2 over L sine n pi x over L sine m pi x over L dx between 0 and L. And this is always 0. And that's not a coincidence. That's true of any mode. So if you have 2 modes of a harmonic oscillator, they're not given by signs, this kind of a gadget, this kind of a integral of a product of 2 different modes will always be 0. Well, technically I should put star, but the star doesn't do anything because these are real. That's why these modes are called normal modes. Because on the one hand, they're normalized, and they're also, it's an example, it's called orthogonality. You would say the 2 modes are orthogonal. It's just like a dot product of 2 vectors. Of 2 orthogonal vectors gives you a 0. Anyway, if this comes out of the left field, sorry for I should not have said that. In any case, this is a 0. So out of those 4 terms, when you integrate 2 of them, it will give you a 0. And the integrals of the others will give you e squared over 2 plus e sub n, I'm sorry, e sub n, sorry, no, not squared, that's a different operation. E sub n over 2 plus e sub m over 2, which is just the average of the 2. Notice that if your prefactors here were not 1 over root 2 and 1 over root 2, it would not be given by this form. And you look at it and you say, wait a second, I knew this. I knew that it should be this answer. Because you told us when you have a superposition state like this, if you measure the energy, you're going to get either E sub n or E sub m with probability given by the square of these prefactors. So the average is one quantity times its probability plus another quantity times its probability, which is what we got. So then why bother doing all this, what looks to you like a horrible calculation, when you can just get the answer? You could glean the answer right from here, right? So average value of the energy equals En times probability of getting the n state plus Em times probability of getting the m state. And I told you that the probability is given by the square of the magnitude of these coefficients. They're real, so it's just the square of these coefficients, which is, you would get, E sub n over 2 plus E sub m over 2. And that's what we got. But this method with the sandwich is more powerful, but because the wave function is not always given explicitly as a sum of the modes. And I give you an example of that in the homework. So in the homework, I'm giving you a very simple example where you have a wave function that just has some shape, upside down parabola. And I say, give me the expectation value of the energy. You see, yes, you can express this wave function in terms of a superposition of modes. That would actually be an infinite sum. You don't want to do that. In this case, I gave you an explicit form of the wave function. And in that case, you have to use this sandwich idea. And the last thing, I promise that what I just told you is method 1. So here, what's method 2? Method 2 relies on the idea note that the Schrodinger's equation, the full Schrodinger's equation, is I h bar partial big psi partial t equals, minus h bar squared over 2m partial squared psi partial x squared plus u times psi. And you say, oh, I know how to write this simply. This is just I h bar times the time derivative of the wave function equals the action of the Hamiltonian operator on the wave function. So the entire quantum mechanics is encapsulated in this formula right here. This is your Schrodinger's equation. And so when you had to operate with the Hamiltonian operator on the wave function, instead of doing it spatially, you could instead do it temporally. So here's the trick, right? So this equals I h bar times the time derivative is 1 over root 2 times psi n e to the minus I omega mt plus 1 over root 2 psi m minus I omega mt, right? Which gives you I h bar times 1 over root 2 Now, time derivative only acts on these guys. It doesn't act on the spatial part, right? And so you get minus I omega n times e to the minus I omega n t plus I h bar 1 over root 2 psi m. And you bring down that exponent. And when the dust settles, I times I is minus 1 times minus, you get h bar over root 2 psi n. I'm going to explicitly write down the omega sub n is e sub n over h bar minus I omega n t plus h bar over 2 psi n e sub n over h bar. These guys cancel. And you get the same result as before. So that's the Hamiltonian operator or the energy operator acting on the wave function. And we got the same result right here. Then you multiply it by psi star, you multiply everything out, you get your 4 terms, you have your 4 integrals, 2 are 0, and the other 2 are very simple because you have this normalization. And at the end of the day, you're going to get this result again. Okay, so I hope I tied together a few things. I have one other bit of information to say about all this. I want to relate what I said today about operators and what I said in my previous lectures about measurements. I want to say a little bit about the connection between the two. And I hope you can see that the details matter. You know, all the meticulous crossing the T's and dotting the I's. That's very important.